if you go to your Blackboard page, you'll see that there are a couple of links that apply to the project. Now here it says data for the project. I don't really want you to use that. I've sent you the data. If you've already used that data, that's fine. But so I'm gonna. How do I do this thing? So I'm going to not display this thing, so you can't see it anymore. You won't get confused. Actually, I don't know how to do that. I'll just delete it. So I'm gonna delete this data so you don't use it. So last week I sent you the data. It has 240 data points. So it does have an even number of data points. So when you're finding the mean and the quartiles, you'll use the same procedure that we went through, where you'll end up averaging numbers to get the median and Q2, and you'll average numbers to get Q1 and Q3. Okay, so use that data. Secondly, the assignment is here, which everybody should have because I handed it out. I also need to replace that with the current one, so I'm going to go ahead and delete that too, and I'll put another one in there. So in case you lose your assignment, I'll post it back in here. I guess the most important thing is that here are the videos that go along with the project. So there's one video that shows you how to do the spreadsheet. There's one video that shows you how it's not verbatim, but it gives you the concepts and gives you enough detail that you shouldn't have any problem answering the questions in the attachment to the original project. And here's the video that shows you how to do a box plot. So you basically have everything you need right here if you need some additional help. This is for chapter 13, which we'll get to in a couple weeks. So ignore that one for right now. Okay, so for you guys who came in late, April 6th is the date for the project to be due. I would suggest you don't wait till the last minute. So if you have a problem, you can come and see me, or you can email it to me. Typically, if you send it to me ahead of time, I'll look at it and I'll say, yeah, that's right, or that's wrong, you need to do this. So you'll have a chance to go back and correct your errors as long as you give me enough time to respond to you. Remember to send it to me as an Excel file, not as a PDF file. I'll have to email you back and say, please resend it to me. Okay, onward. So what we're going to do today is we're going to start on chapter 5, section 5, which is talking about a particular distribution of data. So what we've done so far is we've taken data and we've drawn histograms, which typically show that the median and the mean also correspond to the class or bin that has the most occurrences. So this kind of shape, if you look at a histogram which has a shape which starts out low and then builds up and then comes to a maximum, that's called a normal distribution. But before we do that, before I show you what a normal distribution is, I'm going to do a little point. And we're going to say if you flip a coin 100 times, theoretically, what is the probability of getting 49 heads and 51 tails? What's the probability of getting 48 heads and 52 tails? So I'm going to have a column in my spreadsheet which is n, which is, I'll say x. X is the number of heads out of 100. So I could get 0 heads out of 100 or 100 tails. I could get 1, and so I have all the possibilities between 0 and 100. So like we did the other day, you can easily fill in a spreadsheet by copying. What I did is I put 1 and 2, and then I copied that pattern. And the next thing we're going to do here is we are going to calculate the probability. So this is going to be using the binomial probability formula. So just for you guys who forgot that or never remembered it in the first place, the binomial probability says the probability of x successes is equal to the combination of n things taken x at a time, probability of success raised to the x power, and the probability of failure raised to the n minus x power. In this case, we're going to look at all the different ways of doing it from 0 to 100. Of course, we will not have to do that manually, but we can do it. We can do it using the spreadsheet quite easily. So this is the probability, basically. So we're going to say equals, and there is a built-in Excel function called combination, and you put in the number of trials and the number of successes, which is 0. Shh. Oh, okay. And then we're going to take that and we're going to multiply by the probability of success, which for flipping a coin is 0.5, raised to the x power times, yeah? Oh, okay, yeah. Yeah, remind me about 20 minutes in so I'll do it once everybody's filtered in. Okay. Just don't remind me before the end of the class. Okay, and then I'm going to have 100 minus x. So that's n minus x. So I take 100 things x at a time times 0.5 raised to the x power plus times 0.5 raised to the n minus x power. And so the probability of me getting no heads is 7.9 times 10 to the minus 31st power, which is essentially 0. Okay. And if I copy that formula, well, one thing I've got to do is I've got to, no, that's fine. Okay, so then I'm just going to drag this formula down, and we'll do this 100 times. And so the probability of me getting 100 heads is 7.9 times 10 to the negative 31st. Okay. Now, if you go all the way to 50, the probability of me getting 50 heads out of 100 flips is 0.0795, or about 8%. So if I flip 100 coins, or coin 100 times, the probability of me getting 50 heads and 50 tails is about 8%. Now what I'm going to do is I'm going to plot the probability as a function of the number of successes. So the way I do that is I insert a scatter plot, and I get this curve. Okay, there it is. So what that curve shows me is that the most likely occurrence is 50 heads and 50 tails. And as I go either way, 49 heads or 49 tails, it drops off. It's less likely, but it's almost as likely as getting 50 heads and 50 tails. And once I get down to about 35 heads and 65 tails, the probability is almost 0. And you can kind of see that in the numbers. So if I look down here, and once I get down to about 30 heads and 70 tails, the probability is 0.000023. Very small. And if I go all the way down to 0 heads, I get almost impossible. Okay. The probability of winning the lottery is somewhere about here, maybe there. So getting 24 heads and the remainder tails, the probability of getting that is about as good as winning the lottery, which is hundreds of millions to 1. So if you go this way, it's even more difficult than winning the lottery. Okay, now that shape. Notice the shape. Where did my picture go? It was there just a minute ago. Well, we'll just do it again. Insert chart, scatter plot. Oh, there it is. Okay, so it has a characteristic shape. It kind of looks like a bell, and this is what a normal distribution looks like. So, interestingly enough, the binomial probability for flipping a coin, the curve looks like a normal curve, which has the shape of a bell curve. So, Now, normally things aren't that perfect. This is a theoretical curve, and therefore it's perfectly symmetric. But in reality, real processes, a lot of times the data is distributed in a similar fashion, but not exactly like that. So we could say that as long as the number of occurrences happens mostly near the mean and less often away from the mean, then that would be considered a normal distribution. Okay, so let's go back here now. Now there's two kinds before we get any further along. Shh, somebody's talking over there. I'm going to either turn you down or ask you to be quiet. Okay, so there are two kinds of distributions. There's a discrete normal distribution and there's a continuous normal distribution. What I showed you in the previous example was almost, there were enough data points that it almost looked continuous. It was a nice curve. It didn't have ups and downs. It was very symmetric. And we would consider that to be a continuous, almost a continuous variable. But there are other cases where you have what we call discrete variables. Discrete variables are where they have specific values. So if you said, how many children are born in a hospital each day, those would be discrete answers. You wouldn't have 5.5 children. You'd have 6 or 7 or 12. So that's an example. Usually when it has to be a whole quantity, then it's called discrete. If it can take on any value from from A to B, for example, temperature. So temperature is a continuous variable. We usually measure it with a certain level of accuracy, but theoretically, if I go from my temperature mine's usually 97 point something, to fever, when I go from normal temperature to that fever, I have to go through all the temperatures in between. It's not like I go from 98.6 and jump to 100.2. I have to, it increases over a certain period of time. Okay, so that's what we would call continuous, where it can take on all values. So this is just an example. This is first 6 problems in this section, asking us to determine whether they are discrete or continuous. So the number of heads tossed in 50 coins. So is that going to be a discrete? Is that going to be a whole number? And the answer is yes, because you're not going to flip 2.5 heads. You're always going to have whole numbers. So that would be discrete. Okay. The number of babies born one day at a certain hospital, we just gave that an example. Of course, you can't have half the baby, so that also is discrete. But if you looked at the average weight of babies born in a week, there's 2 reasons why that would not be discrete. Is because, one, it's an average, and secondly, it is, again, weights, just like heights or temperatures, can take on any value. The only limit on how many decimal places the answer has is dependent upon how accurate the instrument is to measure it. So weights, heights, those would be a continuous variable. Likewise, here the height of a seedling, so heights are continuous. You might be limited, with a ruler you can only measure to a certain accuracy, but it's not the variable that's discrete, it's the measurement technique that's discrete. The time is shown on the digital watch. So because a digital watch is only going to give you certain numbers, it's not going to say 11:52.78397 whatever. It's limited. So so time itself is continuous, but the time shown on a digital device is going to be discrete. Whereas the time on a analog watch, when the hand rotates around the face, it's going to take every position around there. It may jerk a little bit, may go like that, but it still has to go between every position. When it goes from position 0 to 1, it has to go between all positions between 0 and 1. So that would be considered to be a continuous Okay, so those are just examples of discrete versus continuous. So what we're going to look at is this, and not just in this section, but the additional material that we're going to cover relative to statistics. The whole concept of a normal or bell-shaped curve is important. And basically, a normal distribution is any random variable, could be discrete or continuous, whose graph has the characteristic shape of the normal curve. So that's one of the reasons I did this little example, is because, you know, this is a normal looking curve. It tapers off to essentially 0 on either side. It doesn't have to be smooth, it doesn't have to be continuous, it just has to have a sort of a bell-shaped curve. It's not a very strict requirement. So let me just draw you a curve that you may not think is not normal, but it probably is normal. It's normal enough. There actually are variables to tell you how normal something is, and you can, but you know, if I drew a histogram of data and it looks something like this, even because of this little blip here, in general it has enough of a shape like a bell that you would consider this to be normal data. Now, so how bad does it have to be so it's not normal? Well, something that would look like this would obviously be not normal, normally distributed. So if you had something that looks like this, you know, that's definitely not normal because it doesn't have a center. It looks more like a U than an upside down U. So that's the point, is that data doesn't have to be perfectly like a bell. It has to have a general shape like a bell to be considered to be normal. And the reason this is important is to be able to apply the techniques in inferential statistics. The data a lot of times has to be normal enough. In most cases, it is normal enough. There's most real things, temperature, height, length of something, you know, if you make something, you're trying to make something to a consistent length, the distribution, because you're trying to make it to a specific length, is in general going to be a normal-ish type curve. So most things are normal. Now there's what's called a standard normal curve, and that actually looks more like this. So if I did the same experiment using 1,000, you know, how should flip a coin 1,000 times, it's even going to have be even more continuous. Here I've got individual data points, but at some point I've got so many data points it almost looks continuous. And you can kind of take that to a limit, or you can do it mathematically, and the curve will look like this one right here. So this would be a normal curve, not a standardized normal curve. It's just a normal-ish curve because it has the shape of a bell. Whereas this curve here, we would consider to be a standard normal distribution. So what are the characteristics of a standard normal distribution? One is it's symmetric. It's actually a continuous line. There is an equation that you can use to define the height of the distance of this curve away from the x-axis at any value along the x-axis. A standard normal curve, the high point here is where you would calculate the mean to be. So it's symmetric, it's continuous, the middle is the mean. And on a standard normal curve, the x-axis is based on the mean, so the mean is right in the middle of the standard normal curve, and then the distances away from the mean are characterized by how many standard deviations. So this distance from the mean is the mean minus one standard deviation, and this distance here is the mean minus 2 standard deviations. And likewise on the other side, plus 1 standard deviation, plus 2 standard deviations. The other thing about a normal curve, the standard normal curve, is that the area underneath the curve is representative of how much data is between two values. So if I wanted to know how many data points or what percentage of the data is between the standard deviation, the mean minus 1 standard deviation, and the mean, if I look at this area, that area is proportional to the percent of data. So what it's saying is most of the data is within 1 standard deviation. Turns out there's 68% of the data for a standard normal curve is within plus or minus 1 standard deviation of the mean. 95% of the data is within plus or minus 2 standard deviations of the mean, and 99.6, I think it is, percent of the data is within 3 standard deviations of the mean. You can see once you get out 3 standard deviations away from the mean, the curve is almost right at the x-axis. So there's very little area left once you get out here or out there. So in section 5, what we're going to do is basically use the standard normal distribution to calculate what percentage of data given a mean and a standard deviation is between two values. One of the cases, another variable or another quantity that is normally distributed is intelligence. So if you look at the IQ test, the mean IQ value is 100. So let's just talk about the IQ, because it's just something you probably talked about at some point. So IQ is normally distributed. The mean is 100. Why is it 100? Because that's what they've set it as 100. Okay, so what they would do is they would take a large enough sample of people randomly chosen of different intelligences. So you don't know their intelligence till you test them, but you just have to come up with some random way of choosing people, and you would test them, and then you would standardize the test so that the average score was 100. The standard deviation of IQ tests is 15. So looking at, and because it's normally distributed and the mean is 100 and the standard deviation is 15, what we can say is that 68% of people have an IQ between 85 and 115. 85 is the mean minus 1 standard deviation, and 115 is the mean plus 1 standard deviation. Another thing you could say is that notice that half of the data is less than the mean because of the symmetric nature of the normal curve. So if you go to, if this is 68% from here to here, then half of that from here to here would be 34%, right? So from here to here is 34, from here to all the way down to here is 50. So what I could say is 50 plus 34, 84, 84% of people have an IQ less than 115. You could also say that 16% of people have an IQ greater than 115. Now, in terms of things we measured in the previous section, you know, an IQ of 115 would be the 84th percentile. That means that 84% of the people have an IQ of 115 or less. So you can relate these probabilities or these percentages to percentiles. You can also say that, so let's do the same thing for so if we had 2 standard deviations, so let's say, so you take the mean plus 2 times the standard deviation, that's going to be 130. And what that says is that you can go through the same thing, or you can do the mean minus 2 standard deviations. So that would be 70. So 95% of people have an IQ between 70 and 130. Now, for the same reason, if I'm just looking at the upper side, so if I have 5% of the people that are less than 70 and plus greater than 130. So that would mean that 97.5% of people have an IQ less than 130, or 2.5% have an IQ greater than 130. So if you've ever done an IQ test and you've scored 130, then you know you are in the 97.5 percentile. And so there's this place, you know, there's this what do you call it? Club. I don't know if it's a club organization called Mensa, which is for supposedly people with high IQs. And I think there is a limit on what your IQ has to be. You know, it has to be above a certain value. That's the only requirement. So let's just search what that is. Mensa IQ score. IQ score, not IP score. Mensa requirements for membership is a score at or above the 98th percentile, which they're saying is 132 on the Stanford Binet scale, whatever that is. Okay, so I just said 97.5 percentile was 130, so it's 132. Anyway, that's just... So you can do that kind of thing with any data. You know, if you looked at probably SAT scores, you would find out that those are also normally distributed, and you could also then see, they probably tell you what your percentile is. It's been so long since I took it, I don't know, but I'm sure there is some data that shows the distribution of SAT or ACT scores or any kind of scores, SOL scores, you know, whatever. Let's see if I can find one here, because most of you guys have taken the SATs or are going to. SAT score distribution 2817. Yeah, so they're showing here percentiles, but it's the same basic idea. Yeah, so these are the, you know, you can look at the percentiles. So the 50th percentile would be the mean, and that is about 1060. Wait, before you leave, okay. So we've talked about 2 specific cases. 1 standard deviation above and below the mean, 2 standard deviations above and below the mean. And I should have handed out this paper today, which I forgot. So we'll just have to, we'll wing it. Actually, I have it in my office. Hopefully I have it in my notes here. Oh, there it is. Okay, yeah. So we'll look at this. We'll use it in class on Tuesday. So let's kind of go through this. We've already talked about it, but let's just review it. The graph of a normal curve is bell-shaped and symmetric about a vertical line through the center. Okay, we saw that. The mean, median, and mode of a normal curve are all equal and occur at the center of the distribution. And then you've got this empirical rule that says about 68% of all data is within one standard deviation of the mean in both directions, about 95% within two standard deviations of the mean, and 99.7% within three standard deviations of the mean. Now in terms of z-score, we talked about z-scores. -1 z-score is one standard deviation below the mean. +1 is one standard deviation above the mean. So you can look at the z-score for data and easily figure out where it is relative to those critical points of 1, 2, or 3 standard deviations by looking at the whole number part of the z-score. And there are various meanings you can associate with this normal curve and the area underneath the normal curve. So it says in the standard normal curve, the following three quantities are equivalent. So the area is equivalent to the percentage of total items that lie within an interval between two values. The probability that if you randomly choose a individual or item that value associated with that individual will lie within a certain interval. Or it's also just the area under the curve is also, these are all equivalent to each other. So we're going to have a table which gives us area, which we can then use to make calculations about these two things. And the way we do that is through this table. So this is a table that I will hand out next time. I'll show you how to use it today. And it's really just a single line of data, but it's put into multiple columns because you go from a z-score of 0 to a z-score of 3 all the way down to the bottom other corner, 3.35. But you go down the first column and you get to 0.55. To get to 0.56, you go to the top of the second column. You go to the bottom of the second column here, 1.1. You continue on the top of the third column. So really, it's just one big two column table where the first column is Z and the second column is A. And we're going to use these areas to then answer questions relative to probability of randomly picking somebody and getting a result, or the percent of values between two given intervals. And if you look at the project that I handed out, you'll notice that the questions that I ask are what is the percent between two values, and so that's the whole idea here. And this drawing goes with this, and what this table represents is not the area from all the way down here up to a given z-score. It's actually the area from the mean to a given z-score. So you can see that the area goes to 0.5 because it's measuring the area from here, this vertical line, to over to there. The total area for the whole thing is 1, so the area of half of it is 0.5. And if we want to deal with negative z-scores, we can still do it. The reason they do that is because you've got a table that's half the size. So the column under area, which is the second columns in the group, gives the proportion of the area under the entire curve that is between z equals 0 right here and some positive value of z. But because it's symmetric, it's also the area from 0 to the same negative z value. So we use symmetry to be able to use this curve for both positive and negative z. Okay, so what I'm going to do is we're just going to look at some problems and use the curve, or use the table, and show you how it works. So I'm going to move this down so we can look at both the table and the question. So let's look at the problem. This is problem 7 through something in the back of the book. So it says, suppose you have 100 geology students measure the mass of an ore sample. Due to human error and limitations in the reliability of the balance, not all the readings are equal. The results are found to closely approximate a normal curve with the mean of 86 and a standard deviation of 1 gram. So what they're doing is they're taking 100 people, they're measuring the ore sample, then they take that 100 data points and they do a histogram, and they look at the histogram and it looks sort of like a bell curve, and so they say it closely approximates a normal curve. Then they take the mean of those 100 student measurements and they get a mean of 86, and they take those 100 measurements and use the procedure we talked about on Tuesday to calculate the standard deviations. So then we have just two pieces of information, not 100 pieces of information, but just the mean and the standard deviation. And we're going to use that information to answer these questions. And then what we're going to do is you take those 100 people and you randomly select one of them. So you put their names in a jar or a bucket, and you shake them up and you pull out somebody's name. And the question is, what's the probability of that person's measurement being between two values, or between one value and greater than some value or less than some value, or between two values. So the first thing we're going to look at is more than 86 grams. And one way to do this is, the best way to do it is to draw figures and try to figure out what they're asking. So I'm going to draw, and you'll see in the assignment that I gave you on Tuesday that I have a drawing with each one of them, and you're supposed to draw, what's the representation. And really what you have to do is, you don't have to be a perfect drawer, you just have to have a reasonably good sketch. And the sketch consists of an axis, a normal curve, a curve that kind of looks like a normal curve. So this is my attempt at drawing a normal curve. It doesn't have to be beautiful, but just so here's my normal curve, and the mean is going to be right in the middle, and it's going to be 86. Now, because of the standard deviation in this case being 1 gram, I could probably just, again, a rough estimate, say that 87 is going to be about right here, and if I go symmetrically the other direction, 85 will be about there. And then if I go out a little bit further, that would be 88. And I would go out about the same distance the other direction, that would be 84. And the reason I'm doing this, if you go back to my standard normal curve, somewhere here, one standard deviation is going to be somewhere to the right. It's not going to be way down here, and it's going to be somewhere in the middle. So I picked somewhere about here, just visually. And likewise, when I went 2 standard deviations above the mean, then I went here, but I left enough so that you could actually see the area. If you go to 3 standard deviations, you're basically going out far enough that you can hardly see anything happening at all. So that's how I kind of just eyeballed my curve here. So what they're asking for is, what percentage is more than 86 grams? So I'm going to mark that by just using a cross-hatching to represent what that means. And you don't even have to use the table to answer this question, because half of the data is above the mean and half the data is below the mean. So when they ask this question, it's just a matter of saying the answer is 0.5. Okay, so we'll say the probability of x being greater than 86 is equal to 0.5. Now let's ask the question: what if it was 80? 7. So we'll kind of go. I'm going to make these up as I go. So the next question is more than. Well, actually, no. Let's not do that yet. Let's do. I'm trying to kind of build up on the complexity here. So what we'll say is between 86 and 87.2. So what's the probability of picking somebody randomly and them having measured a value between 86 and 87.2? Or you can think of it as what's the percentage of people that got measurements between 86 and 87.2. So how do we do that problem? Well, what we do is, because the first number is the mean, and this table is based on taking the distance from the mean, I don't do anything with that one. I just say, well, I could do that. Well, what we're going to do is we're going to calculate the z-score associated with these two data points. Remember, the z-score is the x value minus the mean divided by the standard deviation. So for a data value of 86, the z-score is going to be 86 minus the mean, which is 86, divided by the standard deviation, which is 1. So you get a z-score of 0. And if I go over to my table, it says for a z-score of 0, so let me go over here and blow it up. For a z-score of 0, the area is 0. So then you find the corresponding area associated with this. So the area for z equal to 0 is 0. Then you find the z-score for the other number, which is 87.2. So that's 87.2 minus 86 divided by 1, which is 1.2. And it's easy because we're dividing by 1. So then what you do is you go with this z-score and go over to the table and look for 1.2, which is right there. So here's the z, 1.2. The area associated with z equals 1.2 is 0.85. Therefore, we'll call it the net area is going to be the area associated with z equal 1.2 minus the area associated with z equals 0, and that is 0.385 minus 0, which is 0.385. So that's the math. What does that mean? It means that the probability of randomly choosing a person whose measurement was between 86 and 87.2 is 0.385. Or you could say that 38.5% of the measurements were between 86 and 87.2. Okay, so those are the two ways that you can use the area. So again, what we do is you calculate the z-score associated with the two numbers that define the interval that you're trying to calculate the data for. So you calculate the z-scores. From the z-scores, you find the area from the table. You subtract those two areas to find the net area between those two intervals, and that area is proportional or is related directly to either the probability of picking somebody randomly whose measurements are between those two values, or the percentage of readings that were between those two values. So that's the two ways to do it. Okay. So let's look at another. We're going to do the same thing here for the same data, different question. So let me add another page here. So let's say between 87 and 88.2. So what's the probability of me picking somebody who has these measurements, or the percent of measurements between these two values? So I'm going to draw my curve again. I didn't draw my curve for the previous time. Let me go back and do that. So for this first part, the curve looked like that. For the second part, my curve, my sketch to kind of show what we're looking at is, again, I just draw a somewhat bell-shaped curve. The center is 86. And so I was looking between 86 and 87.2, which is probably about right there. So I draw vertical lines at these 2 points, and the area I was looking for would have been that area. So the area between the mean and 86 is 0, because it's the same point. The area between the mean and this point was 0.385. So I take this area, subtract that area, which was 0, and I get 0.385. In this case, they're both to the left of the mean, to the right of the mean. So here's my curve. The center of my curve is the mean, 86. So 87 is going to be somewhere about right there, and 88.2 is probably going to be about right there. So there, in that case, the area I'm looking for is this area. The problem is that the table measures the area from here, but let me just take that area and move that out for a second. If I took the area from the mean to here, so let me move that out of there as well, okay? And then I took the area from the mean out to this part, which is that area. If I take this area and I subtract this area, that's going to be equal to that area. Okay, so visually what I'm doing is I'm taking this area from the mean to the higher value, and I'm subtracting the area from the mean to the lower value, and that leaves me with the area between those 2 points. Okay, so that's what I'm going to do. I'm going to use the table to give me the blue area and the green area, and when I subtract them, it'll leave me with the red area. So the procedure is the same. You're going to calculate the z-score associated with 87, and we're going to calculate the z-score associated with 88.2. So the z-score associated with 87 is 87 minus 86, the mean divided by the standard deviation, which is 1. And the z-score associated with 88.2 is 88.2 minus 86 divided by 1, which is 2.2. So those are my two z-scores. The further I am away from the mean, the higher the z-score. So 87 has a lower z-score than 88.2. Now with those z-scores, I find the corresponding areas. So the area as a function of z equals 1. So I don't use the data value, I use the z-score. So I go over to my table and I look for a z of 1. So let me put this on one page again. Where the heck did I do that? So I'm looking for an area. I'm looking for a z of 1, and I come down, here it is, 0.341. So the area associated with z equal is 0.341. That's the area between the mean and the first number. And then I find the area associated with the second z-score, which is 2.2. So I go over to my table again, and I go down, I look for here's Z, here's 2.24, here's 1.68, so I go down this column, I look for 2.2, which is right there, 0.486. Okay, so that's my area associated with the second Z-score, 0.28, or whatever is it, 0.486. So you get 0.486. So the area that I'm interested in, which is the red area, so I'm going to put a little R here for a red area, okay? And that's the question, between here and here, is going to be equal to 0.486 minus 0.341, which is 0.145. Okay, so that's the area. So what I can do with that area now is I can say the probability of picking someone whose measurement was between 87 and 88.2 is 0.145, or 14.5% of the measurements are between 87 and 88.2. Okay. So what's another thing could happen is instead of going from 86 all the way to the right, you can go from some other number greater than 86 all the way to the right. So let's look at that case. So what we're looking at is, let's say 87.4, or we'll just say greater than 87.4. So it's greater than 87.4. So what is the probability of picking somebody whose measurements greater than 87.4? What's the probability of, or the percent of measurements that are greater than 87.4? So let's draw a picture and see what that means. So we take our graph, we put on our sort of bell curve. It's getting worse. As you can see, it doesn't have to be pretty. So this is, again, 86 is the middle. So we draw 87.4, which I'm going to say is about right here. So that we're talking about this area right there. So again, just like we did before, we can calculate the area between the mean and this value by using this table. We can take the area from the middle all the way to the end here, which we said was a half. Remember that the green is a half. So this is 0.5. If you go from here all the way to the right, it's 0.5. If you go from here all the way to the left, it's 0.5. So all we have to do in this to find the black area is we're going to take the green area, which is 0.5, and we're going to subtract the red area, and that will give us the, oops, I guess they're attached to each other. That will leave us with the little black area bit here. Okay, and the green area is 0.5. So all we have to do in this case is just calculate, find what is this area, that area, and so what we're going to do is we're going to find the z-score associated with 87.5. 87.4. So that's 87.4 minus 86 divided by 1. And again, you use whatever the mean and standard deviation are. In our case, it's easy because they just pick something easy. So you take 87, well, the answer is 1.4. I don't need to use my calculator. So that's the z-score. That's the red area. So again, I go over to my table, and I look for 1.4, which is right, whoops, look for 1.4, which is right there, and the area is 0.419. So the area with a z-score of 1.4 is equal to 0.4, I already forgot, 1.4 is 0.419. So for my calculation, I'm going to take 0.5, the total area here, minus the red area. So what the red area was, let's pull that down here. The red area was 0.419, and that difference is the little side bit, which is 0.081. I think. Yeah. Okay. So that's the area. So again, what does that mean? It means the probability of randomly choosing someone whose measurement was greater than 87.4 is 8.1. Oh, probability is 0.081. 8.1% of the measurements were greater than 87.4. So again, you can either represent it as the probability or not. Now this doesn't remind me, it means so classes next week so that you can watch them if you happen to be on spring break at Perry McClure High School. So, and also the project is due April 6th. Okay, so we've almost covered all of the possibilities here. We've still got 2 more possibilities. Let's see if we can get those done today. And then we'll look at some general questions. But what I wanted to do today was to basically look at all the different ways that you could be asked these questions. And these are all the ways that you're asked to do it in your assignment. So we've done everything above the mean up to this point. So let's say I want to answer the question between 84.7 and 86.7. Okay. So I've got 1 data points below the mean, 1 data points above the mean. So let's draw a picture that goes along with that. So the mean is here is at 86 again. In your problem that you'll have, your mean will be, actually I just realized that the data set doesn't match the handout. The mean would be 120. So I might have to correct that, and I'll let you know about it. Anyway, just realize that. Anyway, 84.7 is somewhere over here, and 86.7 is going to be somewhere over here. Okay. So I'm looking for the area between those two. So it's going to be this area underneath the curve. So the way I handle this to find this area, so let me pull that out, is I find the area between the mean and the point greater than the mean. And I find the area between the mean and below the mean. Because this is symmetric, I can use the same technique. I just have to use, I'll actually have a negative z-score here. But if I take the red area plus the blue area, that should equal the black area, right? The black area covers the whole thing. The red area covers this side. The blue area covers the other side. And so that's the idea here. So in this case, instead of subtracting stuff, I add stuff. So the first one, we'll calculate the z-score associated with the upper part of the interval. So you've got 80. We want to find the z-score associated with 86.7. That's 86.7 minus 86 divided by 1, which is 0.7. Now, the z-score associated with the other number, 84.7, is 84.7 minus 86 divided by 1, which is negative 1.3. Now, because the table is symmetric, what I do is to find the blue area, I just use the table as normal. But to find the red area, I just use the positive. I'll use a positive z of 1.3 because it's symmetric. So let me just move this down so there's a little space to put my area measurement. So the top area that I'm looking for, this is the blue area. The area associated with z equals 0.7. I go over here to my table. There's 0.7. It's 0.258. 0.258. And the red area, I use the positive z instead of the negative z. So I go over here and I look up 1.3, which is 0.403. So that's the red area. And that makes sense because this is 1.3 below the mean. This is only 0.7 above the mean. So you'd expect this to be bigger than that. So the total area, I'll call this the area, however you want to call it, the net area, is just the area associated with z equals 0.7 plus the area associated with z equals 1.3. So we just add those two together. And if you look at the graph, you can see it's obvious you add them together. So when you add those two numbers together, you get 0.661. So what does that mean? It means that the probability of choosing someone whose measurement is between 80, with the numbers, 84.7 and 86.7 is 0.611, or 66.1% of the data is between 84.7 and 86.7. Okay, so we got maybe two more scenarios to look at before we quit for the day. When we get to descriptive or to inferential statistics, we'll be talking about the same kind of thing, but we'll be talking about specifically about the tails. And the whole idea of inferential statistics is saying if I have two experiments and I get averages for the two experiments and I get standard deviations from the two experiments, can I say that with a 95% certainty, which means that, or 5%, we're basically taking the 5% area in the tails, 95% certainty that the measured difference is not due is not due to chance, that it's due to actual experimental behavior. So we use this whole idea of z-scores and normal distributions and these curves, but concentrate specifically on the ends where you're only talking about a 5% probability. In this case, the 5% probability would probably would be associated with above 88 and below 84. It's on the tails. So inferential statistics deals with the tails of the normal distribution. So we'll see why later, but I just thought I'd mention that today. Okay, so let me go ahead and give you the assignment for this section, which will be due next Thursday, unless you're on spring break and then it's due when you get back from your break. So we'll cover enough material next time to be able to do these problems. So again, if for some reason next week you cannot make it to class, whether your kids are on vacation and you can't get a babysitter, or you're on vacation because it's spring break and you've already made plans, I'm going to embed a question in the lectures from next week that you have to answer and and email me the answer to get credit for attendance, just so that I have some way of verifying that you did watch the videos. And anybody going on trips, I guess Madison, I know specifically you're going somewhere, so have a nice time.